Welcome to the next lecture in our course. In this lecture, we will be trying to cover moment of inertia and gravity. So, the next topic of discussion is going to be moment of inertia. Moment of inertia is a quantitative measure of an object's rotational inertia. It describes how much an object resists change in its rotational speed, angular acceleration when a torque turning force is applied. So, we studied about friction when we studied about reducing friction. Now, we are trying to see a moment of inertia. Why this? That was for a linear, this is for rotational, right. For example, a screw is there or a nut is there. What is the torsional force? When a torque is applied, what happens to the system is called as the rotational inertia. So, here the mathematical expression for moment of inertia I can be represented as summation of m1 r1 square. Moment of inertia depends on two key factors. One is mass distribution, the other one is mass of the object. Objects with more mass further from the axis of rotation have a higher moment of inertia. So, this is what you have played in your school days, right. This is a wheel. So, you stand in the wheel. So, here you have maximum distribution. Objects with more mass further from the axis of rotation has a higher moment of inertia. Think of a dumbbell with weight far apart has moment of inertia. Next is mass of the object is also a key factor. The overall mass of the object also contributes, but with less influence as compared to that of mass distribution. So, mass distribution is an important factor. So, these are the two factors where moment of inertia depends. So, radius of gyration. The radius of gyration is an equivalent distance used to simplify calculations involving an object's moment of inertia I. So, this giant wheel is a radius of gyration. The fan, pedestrian fan, what we have. So, that is also called as here what this is the axis. So, this center portion is the axis of rotation and the bottom one which is there is called as the center of gravity of the entire pedestrian fan. So, the offset whatever is called the radius of gyration. So, the formula will be K is equal to root of moment of inertia I by m. The radius of gyration represents the average distance of all the mass particles in the object from the axis of rotation. It takes into account the distribution of mass and not just the total mass. Big difference, distribution of mass and total mass. So, the relationship between the radius of gyration and moment of inertia is expressed in the formula I equal to m times k square, where I is the moment of inertia, m is the total mass of the object and k square is the radius of gyration. So, moment of inertia also plays a very important role. It finds lot of applications. Flywheel use high moment of inertia to smooth out variation in engine power delivery. So, we will have flyweight attached to the engine. So, it is moment of inertia. Machines flywheels regulate speed and maintains consistent power in the machine. For example, when you have a press, printing press or a press to shear some material from the sheet. So, we always have a flywheel. Pendulum, moment of inertia affects a pendulum's oscillation period. Stable objects, moment of inertia is important for designing stable objects. Ice skaters spin faster by pulling arms in and slower with the arm out. That is also moment of inertia. So, let us look into a simple problem wherein which the concept of moment of inertia will be clear. Find the moment of inertia and radius of gyration of the area shown in the figure about the axis AB. So, there is an axis which is A and B. Okay. So, you have roof which is 1, then we have a box which is 2, and then in the box we have subtracted a radius which is 3. The distances are given. So, let us try to solve the problem. Alpha 1 is equal to half into 50 into 15. What is 50? This is 50 and this is 15, okay, which is nothing but 375 millimeter square. Okay. Then alpha 2 is nothing but 50 into 20, which is 1000 millimeter square. 50 into 20, right. Alpha 3 is nothing but pi, this region, pi into 15 square by 2, which is nothing but 353.43 millimeter square, right. So, now let us try to find out the moment of inertia about the axis MOI about AB, right. So, here it is I AB equal to 50 cross 15 by 36 cube plus 375 into 15 by 3 the whole square plus 50 into 20 cube by 12 plus 1000 into 10 square minus 0.11 into 15 to the power 4 into 353.43 into 20 minus 4 into 15 by 3 pi the whole square. If you try to solve it, what you get is 7.613 into 10 to the power 4 millimeter to the power 4. So, IAB is nothing but 7.613 into 10 to the power 4 millimeter to the power 4. So, this is the answer. The next topic of discussion is going to be gravity. Fundamental concepts. Gravity is the universal force of attraction that acts between any object with mass. It is the weakest of the 4 fundamental forces: electromagnetic, strong nuclear, weak nuclear and gravity, but plays a dominant role at large scales due to its long range and influence on massive objects. So, the universal law of gravitation is very important. It is defined as G m1 m2 by r square. The acceleration due to gravity is always represented as G. The acceleration due to gravity is a constant. The constant acceleration experienced by an object in a vacuum near the Earth's surface when only the force of gravity acts on it. This means an object's speed increases by a constant amount each second as it falls. The value for g is acceleration 9.81 meters per second square. So, some of the applications of gravity: spacecraft design. G is crucial for calculating the launch velocity needed for rockets and spacecrafts to overcome Earth's gravity and escape its atmosphere. So, gravity is very important. Then the satellite orbit, the value of g is used to determine the orbital path and the speed of satellite around the Earth. By precisely calculating the balance between the Earth gravity and the satellite inertia, we can ensure stable and predictable orbit. So, I would request you all to see the recent success of our ISRO and understand and appreciate how is the spacecraft design made and how is the satellite orbit design made. When we are trying to talk about ballistic application, g is a factor in calculation of trajectory of projectile like bullet or missile. By accounting for acceleration due to gravity, we can predict the path and the range. So, now in India we talk about air to air, air to water, water to water, then we try to talk land to land. All these things are missiles. When it moves in a trajectory, gravity plays a very important role. The GPS technology, G plays a role in maintaining the accuracy of atomic clock in GPS satellites. There also gravity plays a very important role. In gravity, we have gravitational potential energy U, a type of stored energy an object possesses due to its position within a gravitational field. Imagine gravity pulling the object down like a stretched spring. The higher the object is positioned, the more potential energy it has, similar to the tighter spring storing more energy. The potential energy is defined as mgh. U is the gravitational potential energy in joules, m is in mass, gravitation g, and h is the object height about the reference point. So, the application of gravitational potential energy U is equal to energy generation, wherein which we have hydroelectric dams use the potential energy of storing water to generate electricity. Roller coaster, the gravitational potential energy at the top is converted into kinetic energy for thrilling rides. So, that is also gravitational potential energy U. The energy storage, pumped storage hydro, acts like a giant battery storing excess energy by pumping water uphill during low demand period. When electricity demand is high, the water is released to generate electricity. So, you can see gravitational potential energy plays a very important role in several applications. As seen in the figure, two spheres of mass m and a third sphere of mass m form an equilateral triangle. The fourth sphere of mass m4 is at the center of the triangle. The net gravitation force on that central sphere from the three other spheres is 0. What is m in terms of m? That we should see. Then if we double the value of m4, what then is the magnitude of the net gravitational force on the central sphere? So, let us try to solve this problem. The first part of the problem is we are trying to solve the distance between any of the spheres at the corners and the sphere at the center is or 1 by 2 cos theta, which is nothing but 1 by root 3, where L is the length of one side of the equilateral triangle, the net downward contribution caused by the two bottommost spheres, each of mass m, to the total force on M4 has magnitude 2 Fy equal to 2 times G M4 M by R square sin 30, which is nothing but 3 times G M4 M by L square. So, this must equal the magnitude of the pull from M. So, 2F is equal to G M4M by L by root 3 the whole square, which is nothing but 3 G M4 M by L square, which is equal to M, right. So, this is for problem A, and for problem B is, since M4 cancels in the last step, then the amount of mass in the center of sphere is not relevant to the problem. So, net force is 0. Okay. So, moving forward, gravity in orbital mechanics. So, we have Kepler's law. These three laws describe the elliptical motion of satellites around a central body. Elliptical orbit, path or ellipse not circle, equal area law, satellite sweeps equal area in equal time intervals, orbital period versus distance, further orbits take longer. So, these are the three laws described in Kepler's law. Moving further in orbital dynamics, the art of trajectory, we have stable orbits, we have gravity assist. Stable orbits are gravity balanced with velocity creates stable orbits. By matching speed and distance, the satellites fall around a central body without ever hitting it. So, stable orbit, this you play with this, you play the gravity balance with velocity creates a stable orbit. So, moment you increase or decrease the velocity, you can try to pull it. By matching speed and distance, satellites fall around a central body without ever hitting it. The gravity assist uses a planet or moon's gravity for a speed boost or path change, here in which it saves fuel on the spacecraft journey. So, here you see how the gravity plays an important role in orbital mechanics. Real life examples are Voyager 1 spacecraft famously utilized multiple gravity assists from Jupiter and Saturn to propel itself further into interstellar space, a testament to the power of orbital mechanics. By harnessing the principle of gravity and orbital mechanics, we can design efficient and innovative space missions, furthering our exploration of the cosmos. So, gravity and orbital mechanics play a very important role in orbital mechanics. To recapitulate what we studied in this lecture, why are the topics of friction, lubrication, moment of inertia and gravity important for mechanical engineers? What is the difference between static friction and dynamic friction? What methods of lubricants are commonly used? What is moment of inertia and why is it significant in rotational motion? What is the universal law of gravitation and how does it describe the force between two masses? How does gravitation acceleration affect free fall objects and what is the value on Earth? Before I conclude, here are the references. I would like to post you some problems for you to consider. The first problem is you try to tie a mass with a string and you try to hold the string by your arm. Start rotating it and as and when the speed goes larger and larger and larger, try to write down what happens to your energy you apply for rotating and maintaining. This will be the and maintaining. So, this exercise will give you a lot of understanding when the object is rotating and with a mass. Now, what do you do is you try to change the mass m1 to m2 and then start doing it. The next one will be try to balance m1 with a string and in the opposite side you have m2 and start repeating the same exercise. Now, you have a detailed analysis of force, energy, what you spend and see how does it rotate. So, this is one part of the exercise. The second part of the exercise is going to be try to pour oil on a small floor and walk on it. So, here the first case is you try to take oil and walk on it. Note down what happens to the friction without the oil and with oil. Now, next what you do is you change oil with water or honey and try to do the same exercise. When you do the same exercise, you will start understanding and appreciating what is the influence of friction, what is the influence of viscosity, what is hydrodynamic lubrication, what is partial lubrication, all these things you will be able to understand. And the next one is you try to jump on the film whatever you created on it and then walk. So, that means to say you pour oil or you pour water on the tile and then you jump on it and then walk. So, here what are you trying to do is you are trying to disturb the lubrication film and then you start walking. So, please try to do this exercise so that you start enjoying the lecture whatever we have discussed. Thank you very much.